So, okay. The title of my talk today is Deep Learning-Driven Combinatorial Optimization and its Applications. I'm Wen Song from the Shandong University, China. So the outline of my talk today is that first I'll present the background of our research, and I will then introduce three major paradigms of the so-called neural combinatorial optimization. And then I will present one of our recent work on learning-based fast online matchmaking algorithm, which is a collaboration research with the NetEase company in China. And finally, I will give some concluding remarks on this, I guess, hot research direction. Okay, so let's get started. The background, I think we are all very familiar with the combinatorial optimization problems, or COPS for short. So in the COPS, we have a set of discrete decision variables and a set of constraints. So our task is to find the optimal solution to optimize the given objective function, which could be minimization or maximization. The most interesting or most hard property of the COP problems is that they are NP hard. So, or mostly NP hard, because the time complexity of finding the optimal solution could be exponential in the worst case, at least for the most cases. Uh, Nevertheless, the COPs widely exist in reality. For example, the graph optimization or vehicle routing problems, production scheduling, and the general problem for formulations of COPs, including the mixed integer programming or constraint programming. The major classes of COP algorithms can be divided into the exact ones and the approximation algorithms and the heuristic ones. So the typical examples of the exact algorithm include the branch and bound and such as dynamic programming. The good things about the exact algorithm is that they have the theoretical guarantees of finding the optimal solutions given enough computational time. But the weakness of the exact algorithm is that it would be hard for them to scale to very large size problems, especially you need to find the optimal solutions. And in reality, many times for extremely large problems, it would be difficult for those algorithms to find even feasible solutions. So the second type of approximation algorithms, they often present as the greedy algorithms. The good thing about the approximation algorithm is that they have a nice theoretical guarantee of finding the near optimal solutions with a performance bound guarantee and in polynomial time complexity. But the weakness or the cons is that we need to have some hard theoretical analysis on this algorithm. So this could be a little bit hard for us to design. And the bounds sometimes could be very loose. And the second type, which is represent a very large volume of methods, is heuristic algorithms, such as construction ones and improvement heuristics and the population-based ones. So the heuristic algorithms have very large practical applications because they have a very good trade-off between the optimality and efficiency. But the weaknesses is that they have no guarantee of finding the optimal solution and it could be slow on some large-sized problems. But regardless of the types of the COP algorithms, the performance of them highly depends on some key decisions. For example, the branch and bound exact algorithm, it needs to dynamically create a search tree during the solving process. So the key question to ask is that at this stage, which node should I create next? For the constructive algorithm, which element should be added to the current partial solution? For the improvement algorithm, how should I change the current solution such that I can find a very high quality solution after the termination of the algorithm? So traditionally, all these key decisions or high quality decision policies are knowledge intensive and time consuming to design, which requires a large time of trial and error to design. And the performance could be limited. Even with such large kind of efforts, the performance could still be limited because of the limitation of human knowledge or experience. So the research question here to ask is that, can we automate the design of the COP algorithm, or at least some key parts of them? Okay. So in this direction, the so-called neurocombinatorial optimization has become a hot research trend. The basic rationale of NCO methods is that for a relatively stable production scenario, similar instances need to be solved regularly or daily. So this gives us an opportunity to use deep learning models to automatically extract useful patterns or knowledge in a data-driven way, so as to avoid the tedious human design and to facilitate the online solving. So the most commonly mainstream approach is the offline training and online solving, which means that we can use historical data to train a deep model offline. The training can be supervised learning or reinforcement learning or imitation learning, so whatsoever, so as to accelerate the online solving on instances from the same or similar distribution. The online solving process could involve some traditional algorithms or just use the deep learning model itself alone. So this paradigm looks very nice, but the key question here is that, does it really work in practice? I can give you a positive answer. It actually works. So later on, I will introduce our work on applying this paradigm to an actual production scenario in practice. Okay. Next, I will present the three major paradigms of the NCO methods. The first paradigm is the so-called end-to-end solving, meaning that from an instance, we just train a neural network to generate a solution without the need of relying on traditional algorithms at all. So this paradigm is very attractive in the beginning, and actually it's the start point of the NCO methods. The typical application of this, or the typical methods of this paradigm, is the transformer-based vehicle routing models. We know that transformer models are very popular in the recent years, and it is actually the core of the large language models that we use daily today. So for the vehicle routing problems, we can consider it as a set of nodes, customer locations. And we can then use a transformer encoder to encode this instance. And then we can use a transformer decoder to generate a sequence of the input nodes, which is just a solution of the vehicle routing problems. So the transformer models naturally fit the solving requirements of the vehicle routing problems. So that's why these kind of problems are very popular in these last 3 to 5 years. The end-to-end methods is their advantage is that the solving speed is very fast, because you can see that from between the instance and the solution, there is only a neural network. So after training, the inference could be very efficient compared to the traditional search-based algorithms. And the dependence on the expert domain knowledge could be relatively less, because we do not need to design many complicated components to plug into the neural network. But it also comes with some costs. So first, the end-to-end methods, they have difficulties in handling complex constraints, because the output of a neural network normally do not have many constraints on it. So its output can be free. But for the combinatorial optimization problems, especially for many practical scenarios, we need to generate solutions that obey many complex constraints. So in that case, the end-to-end methods, it is very hard for them to work, because to let neural network generate feasible constraint is actually a non-trivial task and sometimes could be very difficult. And there will be no guarantee on the optimality for sure, because even with supervised or reinforcement learning, with the current training algorithm, we cannot find an optimal policy. We can only find a near optimal or high quality policy. So there is no guarantee on the optimality. So the second paradigm of NCO is that we can provide one-time input for traditional algorithms. So from another viewpoint, meaning that we can just treat the traditional algorithm as a black box, and then we can use machine learning or deep neural network to generate some one-time decisions. For example, we can generate or recommend a parameter configuration for complex traditional algorithms, such as the MIP solver, CPLEX, or Groovy, or some other algorithms, because the high performance algorithms often involve a large number of parameters. So in many cases, if we only use simply use the default parameters, the performance could be inferior. So many cases we need to manually tune the parameters. But for this kind of task, which is called algorithm configuration, neural network or machine learning models naturally fit these needs. So they can generate high quality, high performing parameters in a naturally data-driven way. So the good thing about this paradigm is that we do not need to change the internal process of the traditional algorithms, because we know that, for example, the complicated MIP solver, CPLEX, and Groovy, or the OR2s. So they are very complicated algorithms, and the internal process is very hard for us to access. So for us to change the internal process, it could be very hard. But we provide a one-time input from the outside can be very easy to achieve. And another good thing that if our target solver or target algorithm is an optimal solver, then providing some one-time decisions from the outside could maintain the optimality if we do not break the optimality guarantee. And the third thing that the learning tasks are relatively easy because we just training a model from outside of the traditional algorithm. But the weakness or the bad thing that we cannot have a precise control of the algorithm. So that's the second paradigm. And the third paradigm is that we can provide the internal decisions for traditional algorithms, or we can open up the algorithm and provide some key decisions by embed a deep pre-trained deep model inside it, so that at each solving state or at some important solving state, it can query the deep network, the deep model to generate some high quality decisions. So this process is naturally a sequential decision-making process because we need to query the model multiple times and sequentially. So in this formulation, we can naturally use reinforcement learning or imitation learning to learn high-quality sequential decision-making policies. So typical application in this paradigm involves, for example, for the branch and bound tree search algorithm, we can learn to branch, meaning that we can learn to select the next node to branch on. Or for greedy algorithm framework, we can learn to construct. We can learn the policy to select the element at each construction step. Or in the improvement algorithm, we can learn how to modify the current solution, which is learning to improve. So the good thing about this paradigm is that we can have a fine-grained control over the algorithm given its current framework. So theoretically, we can learn an optimal policy. But the weaknesses is that we need to access the internal procedure of the algorithm. For the simple greedy or improvement process, this will not be a very severe problem. But for complicated tree search algorithms such as the branch and bound process, this especially for the mature solvers such as OR2 or Skip or Simplex or Groovy, this could be very hard. And many times for the commercial solvers, we don't even have the ability to access its internal solving stage. So this is a third paradigm. Okay, then next I will present our recent work on the learning-based fast online matchmaking. I personally like this work quite much because it actually solves a industrial practical problem. So in this is a collaboration with a NetEase company in China. So we know that NetEase company, one of its main business is online games. So in online PvP games or players versus players games, there is a key component in the online PvP game system, which is matchmaking. So so the matchmaking system needs to generate a matching solution from a candidate pool. Candidate pool is just a pool of players. And each player has its associated feature vector or some properties to describe its feature. And then we need a matchmaking system or an algorithm to generate a feasible matching solution and to maximize the user experiences or the game engagement. But the key challenges in our case is that it is an anti-hard combinatorial optimization because we can actually consider it as an assignment problem, special case of an assignment problem. But it requires a real-time solving because it's online games. We cannot let the players to wait for quite a long time. So we need to solve or to generate a gaming solution, a matchmaking solution within 200 milliseconds. And the second challenge is that the optimization objective here is actually nonlinear because there is no clear linear relationship between the player's features and the quality of the matching solution. Because of this mechanism is actually quite complicated. We cannot use a simple linear function to describe it. So in reality, we can train a player engagement network, a neural network, to predict the quality of an engagement solution. So this prediction is actually quite precise, but to use it as an objective, it is actually kind of challenging for optimization. And the third challenge is that here we have many complex logical constraints. These logical constraints are in the form of the if-then statement. So for example, if in the team a player of job A is for example 2 players, then in the other team there must also be some constraint to be satisfied. So these rules or these logical constraints are designed by the game operators. So they reflect their intention to make the game to be more balanced. So this constraint, we must obey these constraints, but they are in the form of if-then statement. So it could be hard for the algorithm to handle. So in this direction or in this topic, there exists many works that use deep reinforcement learning to generate matchmaking solutions. So they use the step-by-step solution building process. For example, in the right-hand side figure, from an empty solution, it will select a player it will pick a player out of the pool to add it to team A, and then pick another player to put it into team B. and then so on and so forth until all the teams are built. So this process is actually quite easy to understand. This is very intuitive. It can work with a neural network objective because we can just generate a reward after the solution is built. But actually, this framework does not work in our case because the exploration efficiency of DRL is extremely low because the existence of the complex constraints. So if DRL algorithm works, the premises is that we can generate a feasible solution at the end of each construction episode. But for our case, especially for the logical constraints, the condition, so we can only check if the condition is holds after the whole solution is built, and then we need to enforce the linear constraints. So in this step-by-step building process, we cannot guarantee that under the logical constraints, the built solution is feasible. So in that case, the exploration efficiency of DRL is very, very low. So it cannot explore feasible solutions. So the learning signal is actually quite weak. So DRL approach does not work in our case. So how do we solve this problem? We resort to the supervised learning to directly predict the team assignment. So the assignment variable is actually a binary variable. Here the xij, meaning that we assign player I to team J. So this supervised learning task is that given an instance, we predict the probability of being 1 for each binary variable in the optimal solution, which is a probability matrix P. So in this supervised learning paradigm, we do not need the self-exploration as in RL because we can generate the optimal solution or high-quality solution as a training label. But the key challenge here is that how can we obtain the optimal label? How to design the neural architecture to predict the team assignments, and how to obtain a feasible solution given the assignment prediction. So these are the key challenges we need to resolve. So in this work, we propose the so-called MG-mesh methods, which is a multimodal graph learning-based matchmaking algorithm. So it involves 3 stages. In the first stage, we train engagement network to predict the quality of a matchmaking solution. So given this pre-trained network, we then use the Big M method, which is a common technique in the operation research literature, to linearize this problem. We linearize the value units in the nonlinear objective, and we linearize the logical constraints. So in that case, we can obtain the optimal solutions using the MIP solvers. Here we use the skip solver in our work within reasonable time, which is only reasonable for offline training, because for online solving we cannot afford 20 minutes to solve to generate a matchmaking solution. But nevertheless, this efficiency is okay for us to get the optimal solution as labels. And then during the online solving process, given a predicted assignment probability, we define a surrogate MIP problem, meaning that we replace the original nonlinear objective with a learning one. So the intuition here is that we want to find a feasible solution that best follows the direction of the predicted probability vector P. We can verify that if this prediction P is absolutely correct, we obtain the optimal solution to the original problem. So here, the good thing that we, based on this surrogate MIP problem, solving it, we can guarantee the feasibility because the solver takes input all these constraints and to generate feasible solutions. And the solving is actually quite efficient because we are using a linear objective instead of complex nonlinear ones. We do not need to introduce additional variables because big M methods, using big M methods, we need to introduce a large number of auxiliary variables and constraints. So now let's focus on the core part, which is the multimodal MIP solution prediction. So the variable embeddings are the key to achieve high quality solution prediction. So in the literature, there are actually quite a large number of work on using graph convolutional network to encode the MIP solving process. So the normally used technique is the so-called variable constraint bipartite graph. So we can represent a map instance or the solving status of the mapping instance as a variable constraint bipartite graph. And then based on this bipartite graph, we can apply a two-stage bipartite GCN to obtain the variable embeddings. In the first stage, we can just pass the message from the variable to the constraint. And in the second stage, we can pass the message from the constraint back to the variable. And then finally, we can get the variable embeddings. But this method is only applicable to standard MIP problem. It is actually not working on the big M transformed instance in our case, mainly because the M is often a very large value here. So that in that case, the transformed big M, the big M transformed instance cannot be efficiently encoded by this bipartite graph method. So our method is a multimodal architecture. So actually here we have three models. The first is the standard learning constraints. And the second model is that we will use a specially designed, let me just to the next slide. So we will use a HyperNet-based network to encode the logical constraint. So the key idea is that we generate an embedding for the condition first, and then based on the condition, we use the HyperNet to generate the condition for the logical constraints. And then for the nonlinear objective, we use an attention-based team embedding network to predict or to extract the features of assigning a player to a specific team. And then based on all these three models, we can use an MLP to predict the binary assignment variable to get the prediction P. So that's all about our method. And then next I will report the experiment results and the online deployment test of this method. So we use two popular online games run by the NetEase company, which is Dunk City Dynasty and Justice Online. So for the Dunk City Dynasty, we need to generate 3 players versus 3 players matchmaking. And for the Justice Online, we need to generate 12 players versus 12 players. So the Justice Online game is more challenging than the Dunk City Dynasty for the matchmaking algorithm. So the baselines for the baselines, we first use the 2 existing DRL-based method, and then we use a method called OptiMatch, which is also a constraint solver-based method that randomly generates some solutions and then using Google OR tools as a constraint solver to generate the high-quality solutions. And we also include the MIP solver Skip, which is the best performing open source MIP solver today. So we will have 2 versions of MIP. One is we set a time limit. We run the MIP solver. We run Skip solver without time limit, and then we will add a time limit to it to see if the performance could be acceptable. So we limit the because our method takes about 100 milliseconds and 1 second to solve the to generate the matchmaking solution. So for fair comparison, we allow all the baseline methods to generate as much solution as possible and return the best one to as their performance. So from the results, we can see that our method, which is MG match, generates the high quality solutions very fast, within 100 milliseconds. And of course, it sacrificed the optimality because our surrogate MIP problem is not the original one. It's just an approximation, although it is quite efficient to be solved. But we can see that the optimality gap to the theoretically optimal solution generated by the skip solver without time limit is actually not very far away. For the simple problem, density dynasty, the gap is within 1%. And for the harder problems, the gap is within 4%. So the solution quality is actually quite high. We can see that with the time limit, the performance of the skip solver significantly drops. For example, for the harder problem, justice online, skip solver need to find the optimal solution for 19 seconds. But if we impose 1 second time limit, its optimality cap could be very large. And we can also see that the DRL methods are actually not working because of the reason I mentioned before, that their exploration, they cannot explore any meaningful policies because the constraints, the existence of complex constraints. And so the right-hand side figure shows the searching process of our method and the original skip solver. We can see that the skip solver, here the objective is maximization. So we can see that our method reached the high quality solution very fast, but the skip solver, although it can find the optimal solution with 4-second computation, but to reach this optimality, it still requires a very long computational time, which is not acceptable for the online scenario. So this is a online deployment test in the actual production environment. So it involves a 1-week online A/B test. So we set 200 millisecond time limit for each algorithm. We can see that the MG match still achieves the highest number of matches, meaning that it significantly outperforms the existing techniques and generates the highest number of matches. So the online efficiency of this method is also quite fast. It requires less than 100 milliseconds in responding to the matchmaking request. And the inference on GPU is about 40 to 60 milliseconds, plus additional time on calling the MIP solver to generate the feasible solution. So that's all about our recent work. And then I will present some concluding remarks. So we can see that the NCO does work. We can see that NCO does work. It can surpass the human design rules, and it can solve the problem more efficiently, and it can be deployed to real-world scenarios. But still, for this method to be mature, we still need quite a lot of work to do because, from my point, it's still during its infant stage. So one of its major weakness is that it is also one of the hottest topics that the researchers are trying to solve, is the ability to handle the complex constraints. So for this direction, I think a better way is to combine the power of deep neural network and traditional solvers, especially the constraint handling solvers such as the MIP solvers and the constraint programming solvers to enjoy the benefit of both worlds. And the second is that the limitation is that most work are simply just train one policy or just to try to solve one policy of a traditional algorithm. But for complicated algorithm, it often involves quite a few numbers of important decisions. So can we achieve a joint training of multiple decisions to achieve a better performance? That's, I think, also quite a valuable direction to explore. And the third direction is that for a machine learning model to be deployed in the actual production scenario, it will face an open world. So the scenario could change, and the instance itself could be out of distribution. So in order to guarantee satisfactory performance, we need to make the NCO models to have a very high quality out of distribution generalization performance. So that's I think three meaningful future directions to explore. Okay, so that's all for my presentation, and you can access my homepage to see other interesting works. And thank you. Thank you very much.